to illuminate a large chunk of the planet. And for the most part, if you're a human being and you live somewhere that has an address, you're probably dealing with some degree of light pollution. And in a lot of the world's major cities, like you essentially like don't see almost any of the stars ever. All right. So why would you care about this? And originally it was just an issue. It was just a problem for astronomers. In fact, like this was starting in about the 19th century. This is where you start getting some the earliest legislation to deal with light pollution was only focused on astronomy for obvious reasons. You can't see the stars. Astronomers get mad. Most of the time, people don't care. But in small enough towns like Flagstaff, they actually got some laws in the books of like legislating where you can point the lights on the street. And that's one of the earliest legislation. And then later on, there's stuff like Dark Skies Initiative. And again, the focus was still only on astronomy. To give you a rough idea of like what does it look like we zoom in on the U.S. Because the rest of the world is not us. This is extrapolating it back in time from satellite photos and growth models. The late 1950s till we're sort of in between these 2 points now to get a rough idea of like how much this has grown. And again, like if you look at the brightest stuff here, again you're looking at this is about 10 to 15 times brightness of the full moon. So you can see like the eastern seaboard is essentially like it's just having like 10 full moons in the sky all the time forever. And what's kind of crazy about this has grown much faster than population density. So this is not simply, to paraphrase an XKCD comic, this is not just a population density map. This has grown faster than that because there's this cruel irony is that we've gotten more and more energy efficient. We've switched over from incandescents to LEDs. Guess what? If you only need 3% of the energy to illuminate now with LEDs, we just go, well, we can illuminate even more things. So like now, if you go to like, especially go to Koreatown or Hollywood, you can notice this. If you can essentially get 30 times as much light for the same dollar input, maybe we won't use 30 times as much light, but maybe it'll be 20. So the illumination rate is actually growing much faster. And so you can see this, like, this is the Griffith Observatory, like, which thankfully has some stuff that's not dependent on looking at space. But yeah, it was never built to be a real research observatory, so thankfully that wasn't planned. But even in places that were planned for that, it's starting to become a problem, so we can throw stuff now into space. But the problem is, there are other issues that I'm going to get to in a second, but yeah, here in space even, this is a photo taken from International Space Station, Eastern Seaboard. This is a true color photo, which is actually kind of neat. But yeah, scope of the problem, like 5/6, humanity deals with light pollution, 99% of that, like in let's say the US or EU, you essentially like never really see much in the way of any stars. And you are part of the 1/3 of humanity that can't see the Milky Way. And then in really extreme cases, so Singapore is probably one of the more extreme cases, you never actually experience dark adaptation, so your pupils never dilate at night. It's that bright. And actually at really high levels of light pollution, so you experience this in the port of LA, and then parts of the eastern seaboard, Tokyo, Seoul. It is bright enough that photosynthesis can occur. So not high levels of photosynthesis. I wouldn't grow crops by it, but the fact is we can trigger photosynthesis at these levels. So we're talking like 10 times the full moon, 20 times the full moon. Life will find a way. Mm-hmm. But astronomy is kind of the least of it, as we're starting to find out. And astronomy is also a problem where we can solve it by just putting telescopes into space. But it turns out the ecosystem is probably, this is where the bigger issue may lie. Because light it divides up habitats, it's a signaling mechanism, it's really important. Like, I mean, everything, because there's had this like day-night cycle for billions of years, everything's evolved to sync up with it somehow. And so like there's all sorts of issues like navigation, like birds get thrown off by heavy amounts of light pollution. Actually, a lot of research has looked at this with birds specifically because we have huge data sets on them. So captured by community science, there's this whole thing called eBird, where people have just been uploading data now for years. And from that, we've started learning things like birds roost, like their behaviors in urban areas. They behave like they're actually at a farther north latitude than they really are, because effectively, because you have all this glow, the day is longer. So they constantly think they're like 10 degrees further north than they really are. So maybe this has an impact. Maybe it doesn't. And this is one of the big questions in ecology is like, well, does this matter? Are things adapting? And if they are, the next question is like, how? Which is going to be really fascinating. Or is it just causing some things to collapse and other things to flourish? But in navigation, there's always like the sad story that the sea turtles, because they need to, when they hatch, they head towards the So it's all like there's these issues in some places where like okay, like it causes declines in sea turtle population. So there's a lot of other things of this, and the other big thing is that biologically, we're starting to find out that blue light has a greater ecological impact than things like orange or red light, because just it's the color of the sky, and it's just a really ancient evolutionary mechanism that says it's daytime, be awake. And this is actually like why like your phone has a nighttime version now, where you can like at least turn off the blue channel, so you don't stay up all the time, I guess. Although there's probably like other reasons, but like all this stuff is engineered to be addictive, so whatever. But blue light's a problem. All right. So anyway, but it turns out like as we start switching to white LEDs, most white LEDs we're finding out are they're a mixture of yellow and blue, and as we're switching from sodium vapor to white LEDs, again another polarities, we're probably causing a greater ecological impact. Even though we're saving a ton of energy by switching LEDs, now we have this new problem. Although the nice thing with light pollution is that unlike a lot of other forms of pollution, it's relatively a more tractable problem to solve. So saying things like, oh, we're going to decarbonize everything, like, it's not so easy a problem to solve. But if you're just like, oh, blue light caused a problem, like, well, but maybe we should just have some other color, you know, making amber LEDs. So it's at least there's like solvable parts of this, or like, you can think about like, okay, this isn't going to take like 10% of our GDP to re-engineer. So why focus on coastal environments? Well, that's partly because we wrote this grant for NOAA, the National Oceanic and Atmospheric Administration, and so you got to throw in the ocean in there somehow. And since we couldn't afford a boat, the coast it is. Anyway, but no, there's a real reason. So coastal environments, they're interesting because they're intersect between, I mean, obviously terrestrial and aquatic environments. It's where you happen to have, I mean, most major cities now are like on coastal areas, so you're going to get a bias towards this where like, okay, you're going to have like a lot of these urban rural interfaces next to land water interfaces. So we assume this is actually going to be a really common occurrence now in ecosystems around the world, where you're going to have really bright environments on the coast. And so what we want to do is start figuring out like, can we start to tease apart what are the ecological ramifications here, because you're going to have billions of people in coastal cities. There's a lot of life usually also around these coastal environments. So how is everything changing? And so like, because LA is one example of this, but you have hundreds of cities where you have each with at least millions of people all on the coast of the world. So this is a really pertinent problem. So where am I getting data? So we have what's really awesome is we've got some remote sensing, so a lot of satellite-based measurements, and they were never really collected for the purposes of ecology, but they're free, except for one of them, which I'll get to. But we have this satellite called VEERS, which if you've seen most of those Earth at Night photos, it was taken by VEERS. We have another satellite that's much more recent called it's a CubeSat. And I want to get into like, well, satellites are good, except, and then ... And then kind of like what we use these, how we actually use this satellite data in the first place, and then how we use it later on. And then I want to go through kind of like the equipment I used to start taking these photos, and then getting measurements of brightness and all these other sorts of things. So it turns out like the actual equipment to take all this data is relatively cheap. A lot of the data layers are relatively cheap. It's really the time and labor it takes to put it all together that turned out to be the big limiting factor. So VEERS, you've seen these photos. You've seen tons of these photos. Like the famous ones were like, oh look, there's South Korea, there's nothing, then there's China. Isn't that amazing? All right. So VEERS has been, for decades, it's been just taking images of the Earth at night, and it was launched for purposes of things like military intelligence, urban planning, and so on. And so it's just to look at, okay, what's illuminated, what isn't, and well, I'll get into sort of like issues with it, but so it takes all these photos, it composites them, and what it can also do is that it does it every day, but then it does a monthly average where it says, okay, was there anything that flared up for a few days and then went away, like a forest fire? Then it subtracts that out. Then it also looks at cloud cover, and then it can like actually determine like were those clouds, were those not. It can subtract those out, and so it can do these monthly averages and annual averages, where it can composite all these things, and you can get like a good idea of what are the long-term trends. So we're actually using an annualized data layer for this. If we want to get a long-term picture, because we actually use this data to start figuring out where to take our data, and later like why would we bother doing this in the first place? But there's a problem with this. So this data is freely available. If you really, really want, you can download their like half gig TIFF files where they have like 1/8 of the Earth's surface scanned. And this is the smallest data type they have. They don't let you just go like, oh, what does California look like? No, you have to download 1/8 of the planet, and then you have to cut out California, because it's funny. Anyway, so this is what I learned ArcGIS Pro for. But there are limitations for this. One is the granularity. I know what a JPEG is. This is not California. This is Chicago. All right. I should know this. I grew up here. All right. This is Chicago. This is blurry, not because this is a JPEG. This is not a JPEG. This is a TIFF. So it should be clear. But it's not, because the resolution is about 1/2 kilometer. You're wondering like, well, that doesn't sound very good. Well, you build your own satellite. It's 1/2 kilometer because that's actually good enough for the kind of stuff you want to look for, which is like, okay, you're looking at big urban areas. You're looking for things like long-term, like oil flares. 1/2 kilometer is totally good enough for what you're trying to do this. Remember, this was not collected for the purposes of ecology. A lot of ecologists have used this because it's free, you can download it, great, but it's got that limitation. The other limitation is that it doesn't capture the full spectrum. So again, this whole question, like, does blue light have an ecological relevance? It doesn't capture any blue light. It starts at about the midpoint of the visible spectrum, so about 500 nanometers. It doesn't capture anything below that, so it doesn't capture any blue or violet.
Is that linear decision? Like, the blue scatters most of the atmosphere, right?
Yeah, it was partly that, and it was also just partly like limitations that it's made the sensors at the time. It was just easier to do, and there's no spectral resolution. So it's literally, is it illuminated, is it not? Like if you actually zoom in and look at the data files, it's just zeros, ones. Okay. There's no spectral data whatsoever, which is also a limitation. But again, like, that's not why this data was collected at all. It was for a certain purpose, and we can kind of like do some hand wavy stuff, and some ecologists go like, oh, well, it's right there. And broadly, you can use this for like those kind of really big picture questions, but for ecology, it starts to break down.
Is there like other sources you can interpolate?
Ah, I'm glad you asked that. CubeSat. That's right. So this is CubeSat is more recent as we've gotten better with with microelectronics and sensors, and launching's gotten a lot cheaper. We can actually launch a ton of these satellites, each the size of a Rubik's cube. So the Rubik's cube to scale, and we can just put a whole bunch of them and just throw them up in space. And we can actually we can get a lot of really high resolution spatial and spectral data now. These are actually launched for a lot of different purposes, but they're cheap enough now that universities can pay for them. But their big use is still like a lot of military stuff. And actually like the data layers that we're getting, we have to wait for it to be cleared, whatever that may be, because somebody else is using it first, and then they go like, oh, this is fine, you can use it, then we get to use it. So no questions asked. Anyway, so we get it. So whatever they happen to be looking at.
It's like Area 51 like blurred out or something?
It might be. We're only looking at like Southern California coast. I think it's more of just like if there's anything that happened to be of useful intelligence purposes, they're like, wait a month, okay, and then maybe you can get that one. Yeah. So I think that's what it is. Yeah. But we get 16 spectral bands, so we can do hyperspectral imaging, full visible spectrum, near infrared, near UV, and the spatial resolution is 100 meters, so it's actually really good. So I can make out like individual street intersections and all sorts of stuff like that. So way better spatial resolution. So this is really exciting. So this is actually a data layer that we're also looking at. And this you can use to combine this with some other data types to like even build even better models, and I'm going to get to those too. All right, but there's a limitation with taking space-based measurements. Mostly like it's whatever you see from space. So it's like the thing from The Simpsons. Like the only thing we've been able to determine from satellite photos is the $1 trillion bill is not on the roof. And this is a big problem with like if you're looking at really localized light pollution, which is actually like the ecologically relevant stuff. If you think about a street lamp, is that if you can cover the top, and according to space, like the measurements from space, it actually looks pretty dark. But the problem is like it can be really, really bright, and it still has this huge ecological impact. So the thing is, if you start covering lights, and this is like where it's like full cutoff versus non-cutoff, the ecological impact may be identical, but from space, like one looks okay and one doesn't. And this is one of the big limitations of remote sensing is like you're missing a lot of this information, which again is like one of these things where you look and you go like, well, duh, why do I need a bunch of PhDs to tell me that? Well, okay, fine, but like it's one of those. It is an inherent limitation. It's one of the things we're trying to get around because remote sensing is really easy. You throw up a satellite, it takes photos for a number of years, and you just download it. Whereas going out there and taking all the data yourself is really, really labor intensive. So we're trying to figure out, is there a way we can be lazy? Because the satellites are easy and going out there is hard. And is there some way where we can figure out from space what it should look like on the ground without having to drive there all the time? Is ultimately what the end goal of all this stuff is. But we have these problems that we're trying to get around. And when, again, it's just the obvious one of like, well, just because it's bright in space doesn't necessarily mean it's actually that bright on the ground and vice versa. So that's the whole point of this project. And so we're looking at the coastal environment from South Orange County to North Ventura County. And the reason why we determined that is it's roughly the distance one of the professors I was working with on decided is how far can I make somebody drive in a single night. So thank you, Travis. It was Travis, yeah. So it's like, yeah, how far does he want me to drive my Honda Accord and things that I can get back home at night? The answer is North Ventura County. So pretty reasonable. Although there were plenty of nights I got back at 2:30 in the morning, 3 in the morning, and it was like miserable. But it's still like it's doable. So like it wasn't, we weren't going to do like 5 counties or whatnot. So we're looking at, so yeah, all the way southern edge of Orange up to Northern Ventura County, and then what we did is we wanted to determine sampling sites. So the idea is like, in order to build a model of what it should look like on the ground based on remote sensing data, you first want to start with, okay, what are the just choose the locations where we know the remote sensing values. So what we did is we started with the VIIRS satellite data, and we said, all right, this was like, oh yes, I'm finally using like what I'm learning about ArcGIS Pro in my class, and I said, okay, give me every point along the coast, so it's like a couple thousand points, and then randomly subsample them, because I'm not going to do like 5,000 points. To randomly subsample, like 150 of them, and to give me a rough idea of like, okay, give me like 30 bright ones, 30 less bright ones, 30 lesser bright ones, and so on, scattered along the coast to give me a representative subsample from space of like the brightness range of Southern California. And then what we did is we just further subsampled them by what was directly accessible. So some of them, like I could just tell from Google Maps, like there's no way I can get there, because there's some, like there's a naval air base in Ventura County. They're not really, I mean, it's like, I'm sure I'm serving my country somehow, but I'm sure they're not be really keen on me wandering around there at night. And then we just like further just chuck those out. And then there's some other ones like in Palos Verdes that are inaccessible because they're cliff, and I can't take photos there. And this is what our initial site map looked like. So this is a rainbow color schema. And red is the darkest, violet is the brightest, so to give you a rough idea. This is based on the VIIRS satellite data. So this is like from space, these are our brightness ranges. And like nothing too shocking here. So like you have these dark areas over here in Ventura County in the north edge of LA County. So this is like places like Leo Carrillo. There's no major settlements there, it's pretty dark. And then some areas up there in northern Ventura County are also pretty dark. And then like you have some really obvious ones like LAX, and then the port of LA and Long Beach is really bright. It's about 10 times the full moon. And there's a few really bright spots out there in Huntington Beach, because there's some neighborhood that's down there that everybody just had like Christmas lights on. So that, okay. But yeah, this gives you a rough idea of the brightness. Now this is measured in a super intuitive unit scale. Nanowatts per steradian per square centimeter. Anyway, this is just integrated like measurements of light intensity. There's like 50 ways to measure light. I'm not going to go into all of them. I'll just kind of do some hand wavy stuff so you get the general idea of it. But this gives you a rough idea like of our ranges here. So this is about 0 to 2 roughly nanowatts per steradian per square centimeter, all the way up to about 136. So you get an idea of like, it's a pretty big range of brightness values. And I'll start showing like how many orders of magnitude it actually turns out to be.
So you're doing the log 2 scale, right?
Log 2 scale?
It's like 0 to...
Oh, it was with the sampling regime. With the sampling regime, it came out to be roughly that, but it wasn't on purpose. It just turned out to like the distribution fit that for some reason. I don't know.
136 that blew your scale out?
Oh, what was that? It was some point in the port of Long Beach.
A flashlight you set over? Or
No, I mean it's just like you go to the port. It's just it just glows. Like you just don't see anything.
Nice.
Yeah, I mean the port of LA and Long Beach is the busiest port in the U.S. I mean, which is I think 8th or 9th in the world. Yeah, I'm sure there's some town in China that's probably busier, but like anyway.
So you were able to identify the sources of light in each of the
Oh yes, with field work, but this is just from the remote sensing data. This is just from space. This was me not doing anything terribly hard at this point yet. This is just show me like all these points along the coast and what their brightnesses are. And this is before I went out and started taking photos. But this is the map I used to know like where should I drive to first to take the photos. Because what I was doing then is I took a bunch of photos around each of those dots.
So you actually drove to each of
Yes. Yes. So, and Lucy drove with me into some of them, which is also like, and during the summer when the sun doesn't actually set till 10, so that's why I got back at like 2:33 in the morning sometimes, and then had to go to the lab at 9. It's cool. All right.
What were you using to take pictures?
What?
What were you using to take pictures?
Glad you asked. It's a Canon 6D with a modified fisheye lens, and it's calibrated on a mountaintop in Slovenia.
What?
Yes, I will get to that.
Clearly it's not adaptive. It's not like, adapting automatically to the light background.
Yeah. There's the calibration is actually more expensive than the camera.
That makes sense.
Yeah. But yeah, the camera itself, if you really want to do but the camera itself is only about $1,000.
Yeah.
Yeah. The calibration is about 4,000. But if you want to get a camera and get it calibrated, $5,000 you'll get it. All right. So why am I doing this? Well, one of the things we want to show is that, again, this whole question of like 500 meters, it works for some things, but like for ecology it doesn't, and why? At a scale of half a kilometer, you can get turns out you get a lot of variation or variability within even that small area in terms of light pollution. So this is down in Dana Point, and this is a good photo to sort of illustrate. So these are this is just that blue dot there, that's the center of the pixel. And then I just took 5 photos like in that area. And to give you a rough idea, like the difference between dark gray and light gray is about 100. So like a factor difference about 100 in brightness. And here's the great thing, is like all the lamps there are covered from the top. So according to space, it's all dark. But you can clearly tell like when I'm walking, like, oh, where am I near a street lamp? And it makes a huge difference. And it's like a factor, like a difference of 100. It's huge. But this is one of the things where like everyone kind of has suspect this for a really long time with all these like light pollution measurements. Like, yeah, okay, we're smearing out a lot of things. Like, if you just integrate everything in half a kilometer, you're smearing out a lot of data. And it turns out there was a huge amount of variability. Like, I mean, not even just like a couple of percent. It's like, the difference between 1 and 100, roughly. And this is one of the things we want to do is start to improve these spatial models. So we're getting the data for this, and it turns out we got a lot of data to do this, which has been really fun. All right. Here's one of the other tools we did to try to like truth test what we were doing. So we did the photos, and then we use these devices called a sky quality meter. And this is what it looks like. This is not to scale. And this is just one of these things where like the top there is a photo sensor. And the reason why we use these is because, remember, the satellite photos only get the light that's going up straight through the atmosphere. These, we just point them at the top of the sky to basically essentially to check our photos. Because if we point it up there and it says dark and the satellite says dark, okay, it's basically a sanity test. So we did 4 of these at each location to average, and got an average value. And this is like one of our ways to just sort of like cross-check our photos to the satellite. Is this like an extra check?
But you're just going to be getting the light that's bounced back, right? So if it's like it happens to be really dry, really clear,
Yeah.
it should look really dark.
Yeah, but so like when you're talking about like humidity and cloud cover and all that?
So like the light that you're getting from this
Yeah.
is just going to be stuff that reflects back.
Yes, if there's cloud cover. And guess what? We factored in cloud cover and horizon into our models. I'm going to show you that too. So this is another thing we had to factor in. But we did this as a check just to get like, okay, what does the light look at the top of the sky versus the photos versus the satellite? And it's also one of those things you throw in the supplemental data table. If anyone ever gives you grief, no one is ever going to read it anyway. Take that reviewer too. So anyway, we do all this. And these have also been used for a bunch of other projects. So there's the Dark Sky Initiative, and a lot of people have used these. You take these images, not images, but readings of the top of the sky, and you can aggregate them to build these interpolated maps of light pollution. And in this case, about 21,000 so far to start making buildings global maps. And you were talking about well, is there any way that people have integrated satellite stuff with other data sets? And it turns out yes. So using VIIRS, using 21,000 of these pictures, and incorporating an atmospheric scattering model, you can build an even more nuanced picture of light pollution called the Sky Quality Atlas, which looks like this. And if you go to lightpollution.info, you too can look at this map. And they have it all over the world. And it's an interpolated map based on like those 3 data sets. And it turns out to be it's a pretty good interpolation. So this is from 2015. As you can tell, LA is bright, shocking, and it's bright everywhere, except like, and I'll show you some photos like the really dark areas out around here. But for the most part, yeah, LA is just really, really bright. But this is like one of the ways you can start to improve these models by integrating satellite and field data. You start to get a picture of it. And this is all like community science, like basically people just doing this. Click, click, click. All right.
So did you have to make sure that you are taking all the photos at a certain time of the day and season, because I mean, would that be a concern?
Yes. We have a whole standardization procedure for this. So this is also one of the reasons why it's really tedious to take these photos. It turns out as long as you're taking these photos after true night begins, you're okay. But one of the things we did was we also like made sure like all the images are done in this like really standardized way, and I'll actually go through that procedure really quick. But as long as it's after true night, and like this is where one of the things where, thanks to this project, I got really familiar with the lunar calendar and what night actually means, because what everyday humans call night apparently isn't night. So one of these things where you have like when the sun sets, and then there's when it goes 3 degrees below the horizon, and then when it goes 6 degrees below the horizon. So I have like civil and nautical twilight and astronomical twilight. So we had to wait till it was like far enough below the horizon. So I had to look at when does the sun set, and I had to look at like, okay, what's the time after that? And what would really suck is like with timing traffic is sometimes I would get there early and I would just have to sit there and wait, even though it was dark out because it wasn't real night, which was like, that was fun. So that would happen, and then there's this whole thing. I'll show you like the other standardizations we had to do with the images. It turns out the actual time of taking photos was maybe like 1/6 the actual time of like driving, calibrating, all that stuff. But anyway, so the camera equipment. So we used a Canon 6D, really cool camera. There's charge coupling devices, so they're just high-end digital cameras, and we're using these because we're getting these whole fisheye lens, like pictures of the night sky, and I'll show you what those look like in a minute. But you get the whole image of the sky, you can get all the color data, you get the whole distribution of all the different brightnesses, so you get this really, really rich data set. And then you can use it to start building these really nuanced models that tie in together things like how bright's the top of the sky, what does it say from space, what's the amount of cloud cover, how much stuff is blocking the size of the image, and so on. And what's the color spectral distribution. So that's one of the other things we're kind of interested in doing that like nobody's done yet. Here's the protocol. That's a photo of me. Okay, so this was actually taken in Oxnard. So the way that we did this, as you see there, so that little like green bubble level there, the camera has to be perfectly level, and there's a compass on it, so the top of the image always is facing north. And the reason we do that is because when I upload the images and then start doing analysis with them, the image analysis software looks for the 30 brightest stars, and then automatically then readjusts the camera image so that everything is absolutely oriented the same way. So that when I look at one image taken in northern Orange County and one image in LA County, they're all exactly the same in terms of their orientation and leveling. So that the top of the sky there is the top of the sky there. And this is a really, really tedious process, because at each location, each pixel, I did this at 5 different points. So I would take photos, walk 50 meters, set up and calibrate again, take more photos, and it wasn't just one exposure either, it was multiple exposures, because the other thing we had to standardize is get just to the edge of saturation. So the idea would be like, when you take photos and you expose them too long, you start getting saturated pixels. But the problem is that once you get above saturation point, you don't know how to calibrate. So because if it's beyond a certain scale, it's just you don't know what the reference is. So what I do is do multiple exposures where I underexpose and overexpose and do multiple ones. So I can get just the point where like a few pixels start to saturate, and I would always use that exposure. So again, then like I can compare images, and I know, okay, like these are all done roughly in the same range of exposure. So in really, really dark areas, I would take up to 2-minute exposures. In really bright areas, as low as 1/300th of a second. So like Port of LA, I got down like 1/300th of a second. Places like Leo Carrillo, I got down to like I think I got down to about 130, 140 seconds. Huge range. But you're doing this just to get to the edge of saturation. So I'm going to calibrate all of that.
Using the camera histogram to figure out saturation?
Yeah, get the camera histogram. But I did multiple ones, and then I wrote a Unix script, because anything less is for failures, to scan through each image, count the number of saturated pixels, and then automatically select the optimal one. That was cool too. Unix is great, everybody. Okay, so
What was your way of defining
yeah.
what would be distinguishing from the other sources of light to, I mean, to just capture the man-made light compared to the
Okay,
light?
so this is this is something that I didn't do the calibration for. So the camera. So this is one of the things is like, how do you know it's really just light pollution? And so one of the tricks is with a camera, when we first bought it, we send it over. So there's a lab in Slovenia that does this calibration work and also built the software that we're using. And the reason why it's in Slovenia is most ecological light pollution research is done in Germany for some reason, and Slovenia is near.
They care.
I guess because they care. Yeah, I mean, I don't know, and we don't. And Slovenia, which is a country that's younger than me. If you've ever heard of Yugoslavia, it used to be part of that. Doesn't exist, doesn't matter. But like the whole thing is like, they calibrate this, and what they did is they would take these cameras, they would set up and do multiple exposures in an area that had no known light pollution, so like just up in this remote mountaintop, and they would do the exposures, and the reason they were doing that is because one is to know what does true night actually look like on the camera. So you know you have a reference point for the camera, and that's actually programmed in. And the other thing you do is because every camera has a unique noise fingerprint. So your CCDs in your camera, and your phone has this too, will trigger on infrared. So you actually have, your camera actually has all these like software that's in there to try to filter out all these like erroneous triggers, because heat will cause like the CCD to trigger sometimes, and like say like, oh, that pixel's on. And so one of the things we do is when we take photos, let's say it's a 5-second exposure, I would take a photo, and then there would be something that would cover the CCD, but then we would let expose for another 5 seconds with no light coming in, so that we could record what the noise was, and know what the noise was at that time, and then subtract off the noise.
You ever thought about looking for cosmic rays using this?
You are aware of what I used to do, right? Okay. Anyway. Yes. Anyway, in case those of you on the internet aren't aware, I actually used to do physics research, and one of the things I used to look at was cosmic ray trigger on CCDs. Brad. But that's not really important for what we're trying to do. But actually, we do account for that, because during the noise calibration stuff, that's if we happen to get cosmic rays, we just subtract those out too. So we did four of those like sky quality readings per location, so that turned out to be like 20 per pixel. And we did 4 of those and averaged them, and that gives you this like rough idea of what's called limiting magnitude at the top of the sky, so how bright the top of the sky is. And usually got 3 to 4 exposures. And one of the crazy things about doing this project is I got thousands and thousands of times to practice. Like, if I know how dark it is, I know how long to expose things now. It's really cool. It's like a superpower. So if you just take me anywhere, like I know like, oh, you can do like a 5-second exposure. It's really weird that you can start guessing that. Also knowing where true north is. I got really good at that.
Did you do lens corrections after the fact?
So we did that. That's also part of the calibration for using this fisheye lens. We had to also factor that in as well. So yeah, the calibration is like by far like the most tedious process, like to get the camera ready to do the photos, and then every time I took a photo, it was like a couple minutes to just run through and do all that. So this was like, even after like driving 2.5 hours in traffic getting somewhere, and then like sitting there and then like making sure all the stuff was set up. So, which is also one of the reasons why it would really help to have people come along and help me. So,
I guess I'm saying after you take
Oh.
the image,
Yes.
are you doing a post-processing lens correction?
yeah, in the software, yes. Yeah. So this is when the images come on the computer. This is what they look like. So it's the fisheye lens here. This is just give you some like rough idea of the photos. This probably doesn't look too good with. Let me just see how this looks.
So your saturation, is that like, you were looking for 250 in all 3 channels, or you're looking for...
255 in all 3 channels, yeah.
So you could get like 255 in the G or the D, but you don't call that saturated?
Yeah, we won't call that saturated. It has to be like white saturated, yeah. So I'll turn the light back on in a sec. But so this is Leo Carrillo. This is the Milky Way, and this is maybe not be so clear, but it's me, my wife, and one of our friends. This is in northern Ventura County, and what we did is we set up a 10-second exposure so that we got the stars behind us, and we're just standing over the camera. It also gives you a rough idea of like the fisheye effect, so the Jimi Hendrix Experience kind of image. And This was done when Mars was at its closest approach last summer. So this is in July when we were having like 115-degree days. It was 95 at night on the coast then, at midnight. These were some of the coolest photos we took because we got stuff like shooting stars and like at the Milky Way. That was a lot of fun. And this actually this area also got really damaged by the fires and like some landslides recently. Because I went back and took some more photos like in that area, and like one of the places I parked at in the summer had like collapsed into the sea. So that was exciting. But yeah, and then you can also see in this other one on the right, there happened to be, we timed it so that the Shoreline Express was behind us, so the train wrapped around the horizon. Anyway, that photo was like, that one's really cool. But there's kind of a scientific reason, like I took that photo and I'll explain why, just besides like, other than like, that's kind of the neat trick. So.
What was the focal length of that lens?
It's 2.8.
Not the average.
So the ISO 1600. I'd have to go back through the metadata. ISO 1600.
The lens, like, is it 14 or 12? They shy are usually 12, 14.
I think it's 14. Yeah, that's like one of those things I forgot. Like that's like in the metadata somewhere that I think that's what it was, but I'm drawing a blank. The ISO 1600, f2.8. Everything's kind of like set to like look at infinity. And I wrote it all down. I can show you the whole file. Okay. So here's some more. Turn off the light again. Here's some more great photos of things you can't see. Okay, so this is. You look here. This is again. We got a lot of stars, but these are long exposures. Like this is like a 45-second exposure. So if you were out here at night, this actually looks really dark. But you start to get the saturation, and this whole thing around the horizon, this is what we call sky glow. So this illumination in the atmosphere is scattering off of moisture. The humidity was actually really high at this point. You get this idea of like, okay, like this is how we can get light pollution carries over. It's actually one of the issues with modeling light pollution from just remote sensing, is that you may not be in an area that looks dark from space, but because of sky glow, how far the light can carry, you can be like 200 kilometers from a place, and you still have to deal with the effects. In this case, we're maybe like 10 kilometers from there, but like it carries over a good deal. Then you can also get some really interesting cases. This was in Redondo Beach, where again, top of the sky is really dark, and according to our sky quality meters and satellite, it's dark. But then you get this huge amount of direct glare from a couple of dedicated light sources. They're pointing straight down at the beach. This is actually this is a restaurant, Redondo Beach, where they like had floodlights on the beach itself, because people want to look at the waves. And we were sitting there taking photos. So, but yeah, the top of the sky looks totally dark. Nothing's pointed up necessarily. So, and then this is like, again, like going back to some of these photos here. Just to give you an idea, this is like an over 2-minute exposure. This really bright point here is just that every once in a while there's a car on the Pacific Coast Highway. But over a 2-minute exposure, that's kind of that's like the aggregate like ecological impact. You start to see it, and this glow over here. Remember, like we're 100 kilometers from LA. This is the sky glow from LA. Again, according to space, like we are nowhere near any place that's bright, but it like just carries over. Even like if you're in Death Valley, you get the glow from Las Vegas.
Big time.
Yeah, I mean it's just like it's just something you just throw out there and it scatters off the atmosphere. So.
So you're saying that if it's true light and you know how to take photographs.
Yeah.
You can capture Mars and all these stars on your camera.
Yeah.
With that kind of light.
Yeah, it's so if you're out here, like it's really really dark, where we were, but like this is like integrating it for 2 minutes. So this is like if you add up 2 minutes worth of light. I mean, think about like how quick a normal photo is when you take on your camera compared to this. Like if you just took a 2-minute exposure on your cell phone camera, it would just completely wash out. It would just be all white. So this gives you like how dark this is. And this turns out to be roughly 1/10 billionth the light that you experience at the Port of LA. Which also gives you some rough idea of like how great the human eye is at adapting to ranges of brightness. Because you can essentially, like, because your pupil dilates and you can sort of calibrate for that, the human eye can like adjust to this, like, something like roughly like 100 trillion changes in order of magnitude in terms of brightness. So this, where we were here, you could see the Milky Way with the naked eye. There are a couple of places where we actually got the Milky Way on camera with like a 30-second exposure, but you wouldn't be able to actually see it with your own eye, which is kind of interesting, because there's sort of a limit to like how much like the eye can adjust to it. But yeah, like, I mean, Mars was at closest approach was bright, but you start seeing like a 2-minute exposure, like it starts to really illuminate because you're integrating over all that amount of time. But yeah, this is 2 minutes. That one's 10 seconds, which just makes like the whole train like really light up. So, okay, so like, what does this mean scientifically? Other than like, I have like a couple of thousand really cool looking photos. One of the things is like one of the questions we wanted to do is figure out something called scalar illuminance. So scalar illuminance would be, imagine so you have all this light that's coming at you. You're standing at the center of this hemisphere. If you were just add up every photon that bounces off of something and hits you, that's scalar illuminance. Just add them all up. So, you know, you just integrate over pi r, anyway, whatever. So I actually did have to use calculus for the first time in a decade for this project. It's amazing. One of the other things we want to do is start looking at how do clouds and structures affect brightness on the ground. So this is a question that like it's hard to get at from space, but like when you're sitting there and like you're looking at okay, how much stuff is like overhead? Are the clouds reflecting light back at me? And then the structures, are the structures blocking light? Are they reflecting it, and so on? And then one of the things that people really haven't looked at yet, which is color temperature, which is are we experiencing blue shifting of light pollution? So we're getting enough photos now where we can start to answer these questions. Like we have the switch from amber lights, which are mostly sodium vapor, to LEDs, which have a lot of blue light in them. And this is one of the things we can start measuring. And one of the things we've actually started, if you look at time-lapse, like over years of photos, like in places like LA, you actually start seeing a blue shift in light pollution because as sodium lamps burn out, we just slowly start replacing them with LEDs. It's like over time, you start seeing the neighborhoods start to shift from like orange to like white, which is essentially yellow and blue. And it's kind of cool looking, but like this may have like some other side effects. The other things we're doing in these photos is we want to address this idea of spatial variability. How much does this change within a 500-meter range? And the answer is it can change a tremendous amount, but it depends on some part of it depends on some factors in the landscape, and this is one of the things we started figuring out how to model this. And the hemispheric variability, which is, if you look at this photo, it's actually got a lot of what's called heterogeneity. It varies a lot. Some parts are incredibly bright, and a lot of areas are just super dark. And how do we quantify that? So this is like, how variable is this across the hemisphere of the sky? So like, actually this is some of the astronomers use when they talk about the afterglow of the Big Bang. They talk about like how much like variation you see in that background, which is total overkill for what I'm trying to do for this project, but like, I majored in physics and people must know it. All right. So this is what the computer spits out when I look at a photo. Wow, that makes sense. Okay, look at it. So this is the actual, this is what they talk about the scalar illuminance. This gives you the illuminance of like each little area of the sky. And then we can just integrate all this. You'll get what's called the scalar illuminance, just that simple number. And then on the right there is the color temperature. And generally the color temperature, if there's no cloud cover of the top of the sky, is actually really high, which means it's like towards like blue and violet. Then generally like a lot of like traditional light pollution is over towards the red-orange part of the spectrum, although that's been changing. So this is the kind of stuff we get. And then also we can calculate if the image is getting too saturated. There's all sorts of like fun data that we can pull out of this stuff. And then there's a newer camera that we got after I finished taking all my photos that automatically took GPS. So that automatically like stamps all these things. So because the whole time I was doing this, I had to use my phone and then like get a GPS lock. And I don't know if you know about this, but like to save energy, your phone doesn't just keep a GPS reading going all the time. So every time I need to get a GPS reading, I have to sit there and I had to wait for it to like, oh, it has to reconnect to the satellites. So like, we just talked to the satellites 5 minutes ago, and it has to wait for it again. Whatever. You need at least 4 satellites to tell you where you are. It has to do with general relativity, believe it or not. Okay. So this is the kind of stuff I looked at for weeks and weeks and weeks, and did a bunch of analysis. And this is a final product. I made this map in R. Okay. So what is this? This is, remember if we went all the way back to the original sites? This is the actual data I ended up taking. And again, the color scale here, like red is darker, violet is brighter. This is on a log scale, to give you a rough idea. So this is about a factor difference of 300 between the red and the violet. So to give you an idea of like how much variation there is. And this is illuminance, this is in millilux. So this is, to give a rough idea here, so we're talking about 100 millilux is roughly a full moon. So if we're going up to like 10 to the 3.5, or like talking about 300 millilux, you start getting an idea of like ranges of brightness here. And you can see these are all the sites I ended up taking. So this turned out to, the end product of this was 103 sites Each site had 5 locations where I took photos. Each location I did about 3 to 4 photos. So you get about roughly close to 2,000 photos at the end of all this. And here's where I got all the data. There are a few gaps for practical reasons. This is military base. This is Malibu, which is really hostile. And then somebody please verify that we did get yelled at. Okay, so anyway, we got a few photos of Malibu. That's all we managed to do. This is Palos Verdes. It's mostly cliff. There are a few places I could kind of get down to the coast, but most of the places in Palos Verdes is just like sheer cliff in the ocean. And then
And you wanted to be on the surface? You wanted to be at ocean level?
Yeah.
Okay.
Yeah. So that was kind of there was actually like this one place I went to here where it was like a gated community. And it's like, oh, can I get to there to take photos? And I was like, the guy just looked at me like I was crazy, and he just pointed, and I looked down, and it was just like rock and then water. I'm like, okay, never mind. And then what was there was one other. Wait, what?
Laguna further south.
Yeah, that was just because of the sampling schema. We didn't end up having a lot of there weren't a lot of pixels there originally, which is kind of annoying because that was actually pretty easy to take photos. But whatever, that's what the random number generator gave me. So for the most part, though, I got the entire sweep of all 3 counties. This is about 6,500 miles of driving. It's about 7 months of field work.
So how to correlate with the satellite?
Okay.
Oh, and also,
Yeah.
has anybody ever yelled at you for using rainbow color scheme to represent linear data?
So I was just having this conversation before you got here.
Just do not do that.
Sorry. Anyway, I know I'm using I made this earlier, but I'm gotten into using this Viridis color scale
Okay.
for some other stuff.
Alright.
But
No.
what? I mean, come on. Look,
I mean,
red is
yeah,
dark. What?
Pride and all, but no.
Whatever. I'm proud of it. Okay, so this is you start getting the values in again. This is so SKM is a sky quality meter. That's the thing. I'm pointing at the top of the sky, and in this case, so again, so red is this one's the reverse because sky quality meter again because this can never be intuitive is a negative log scale, and so limiting magnitude. The way it works is the higher the number, the darker it is. So really dark areas you can get to 21, 22. So places like Death Valley you can get to 22. Leo Carrillo we got close to 21. Port of LA we got all the way down to 9. So about a range of 1 trillion differences in magnitude, which is gigantic, especially when you consider how geographically close all this stuff is. And we even got stuff a factor of the difference 100 brightness even within a same pixel. But remember we just smeared all the pixels together and said oh it's all the same. So this is what we got looking at just at the top of the sky. I'm just going back and forth like this. And one of the things I want to show you is the scalar luminance. This is the true data integrating everything in the images. There's way more variation here than if you look here just at the sky quality meter. The sky quality meter is much more indicative of what you see from space. Because the top of the sky, remember, when you see it from space, you're really only getting the top of the sky, and it looks way more uniform. And you're missing a tremendous amount of data that way. And that's one of the things we started learning doing this. And then, just because this has nothing to do with the actual analysis for what I'm going to do next, here's the sky quality temperature. And this is all over the map, and it's mostly because different towns on the coast are at different points changing their street lamps. And I thought maybe there'd be a trend, and no, it's pretty much, I think the way all towns work is whenever the lights burn out, that's when they change them. So this is literally just a random failure map. It's whenever that burns out, you swap it out. But I thought there would be a pattern, and nah, it kind of looked cool, but I made the map. All right. So all of this is going towards building a better model because as you can imagine, driving 6,500 miles to do all this is a tremendous amount of work. And if you want to look at ecological impacts of light pollution, you probably won't have to keep doing this every time. So what we want to do is start looking at can we use any of these remote sensing data sets to build a model of what we should see on the ground? Basically, is there a way to take what we see from space and then build some sort of fancy equation that says, okay, this is what you should see here. And we're using the VIIRS satellite data, and then we also looked at the Sky Quality Atlas, which is where you use VIIRS, and then you use the Sky Quality meters, and you use the atmospheric model. And then one of the things we want to look at is what's affecting how much it varies within a pixel, so spatially, and how much does it vary across that whole horizon. So we want to look at cloud cover, so what percentage of the sky is covered by clouds, and then horizon cover, which is just basically anything in the dome of the sky that's blocked by a building or a street lamp or a tree or whatever is blocking the light or reflecting the light or something like that. Sorry, everything's going to be rainbow scheme. Just deal with it. All right. I didn't know about the Viridis R package until like 3 days ago. Okay. So don't worry. The next paper I'm working on, I'm going to use that schema. All right. What is this, Brad? Okay, so this is I log scaled this, but this is a comparison of the scalar illuminance. So the y-axis is our data, the bona fide data that I spent all those months getting photos of. And the x-axis is the Vir satellite, and it's basically saying like, okay, in general, if it looks brighter from space, it looks brighter on the ground, roughly. And that's what like if you just fit like this sort of simple little linear model to like, okay, generally like if that gets brighter, that gets brighter. That makes sense. But you can probably tell like, I'm not even going to talk about the statistics on this stuff yet. There's a huge amount of scatter. All right. This is obviously not that great of a model. You just know like if it's brighter from space, it's brighter on the ground. Great. I could have told you that before I drove for 6,500 miles. And if you look at percent cloud cover, that also doesn't seem to have much of an effect. It's just like completely all over the map. Cloud cover doesn't seem to have much of an effect on how well these two things are related. It turns out like we thought initially when we did all this that clouds would really matter, and they don't seem to. It's strange.
It looks really clumpy. Is there any, are those clusters like anything, or is it just they're reflected near the same place, or?
It's just like a lot of, clustered on the x-axis or y-axis?
X.
Well, shouldn't they?
Should they?
I mean, you're saying upper radiance versus the scalar illumination P was 40. I mean,
Well, I mean,
Like if you look over to the far right, it's like.
you're actually more. It's more thrown off by the fact that you have some super bright stuff
right.
over here.
Yeah.
Whereas like most of the stuff, like even the areas that like you consider light polluted are still like really like mostly up to this point. It's only like the thing that really stretches the graph out is there's a handful of stuff that's like all the stuff like over there is mostly like LA Long Beach. That's what stretches it out. So it's not really more clustered. It's just why those things are way out there, and just because the port glows like the sun.
Okay. You're asking why the dots are all in a vertical line. Is that
In part, yeah.
is that from the scale that you're getting from the Vir's data?
Oh, why is it like this?
Yeah.
Oh, because you have 5 photos for each site. So
I got
So
you.
this
Yeah.
is per photo, not per pixel.
this is per photo, yeah.
Okay.
Yeah. So this is 515 data points. The hardest 515 data points I've ever collected. Okay. Now this is horizon, percent horizon. There's a clearer picture. So how much of the sky is blocked by some horizon structure does seem to have some sort of significant role going on here. So if you have nothing really blocking it, the sky's darker than what you expect, and you have stuff that's blocking it. And the reason being is because things that are blocked, like on the edge of the horizon, generally in our environments are one of two things. There are a few exceptions to this, but for the most part, they're either structures that are reflecting light in an urban environment or direct illumination. And so it just tends to shift everything up. So it looks brighter than you'd expect in space. So that's one of the things we started figuring out from this. But again, like, it's still kind of crappy. Like, I would not ever say this is a linear relationship. This is just like simplest model, and I can just tell you like they're generally positively correlated, but it's really crappy.
Would it be better if instead of taking those 5 data points which are sort of saying the same information?
Yeah.
And
Collapse and do error bars. I thought about
not error bars, but maybe just one point so that you're not confused. Because basically your idea of taking 5 photos was to like be sure about what data you're collecting for that.
Well, no, it was actually also I wanted to get an idea of how much variation there is within each pixel.
Yeah, but when you're looking at the linear relationship or when you're studying that,
Yeah.
I think it would make the picture more clear as to, as to what you're trying to kind of.
Yeah.
I mean, I'm just thinking aloud about it.
No,
So,
statistically, you're right.
yeah, statistically, I mean, that would make more sense because that's
Right.
what you're more interested in. So, median value or some.
But one of the points is already that the pixel oversimplifies the data. So if you have multiple pictures per pixel, and since the Vir's data is per pixel,
Yeah.
then this shows that there's a lot of variation even within, the single Vir's data.
Yeah, I didn't want to dump out the variation yet
Yeah.
because I wanted to show like how much, because I wanted to illustrate like you have this huge vertical range, this huge range in the actual what we're actually seeing within each pixel compared to like what each pixel says.
But when you're
Yeah.
fitting a model, how will you handle that? Because I mean, would you have to think about something for each data point, or I'm
These
just
are
trying to.
Oh,
These are
because I'm not
general.
going to be using just veer. Well, that's one of the things I'm getting at. It's like why I'm not going to use just veers. Yeah,
Oh, okay.
yeah, yeah.
Yeah.
So because it would be a terrible idea just to fit it from this one parameter. This is part of the reason why, like,
No,
yeah.
I mean, I'm just even pictorially, I think
Oh,
it
yeah.
would make the. I mean,
Oh.
if we just had that, maybe it
I
would.
see.
With
But
pseudo
that's just,
replication,
yeah.
you would like specifically use like a random effect model that with like position as like your random effect, and that would calculate variance within each location.
Or I just get other brightness data that's associated with a higher like spatial granularity and use that to which is what I'm going to get to.
Okay.
Yeah. I guess this is a crappy fit. All right, moving on.
It's pretty good. You probably got like what? You probably got like an R squared of about 0.3, 0.4.
Holy shit. You can just eyeball that and just yeah.
That's annoying.
Okay. Yes.
Not my first rodeo.
All right. Okay. I see you two are well trained in the ways of science. All right. Now we can get an improved. This is actually like an improved model because now we're using a couple different parameters that have higher spatial granularity. So the sky quality atlas uses veers and it uses all the local data from sky quality meters, and it also uses an atmospheric scattering model, and the correlation improves. Again, cloud cover doesn't seem to help that much. So again, this is our data versus the sky quality atlas. The correlation improves. By the way, like I'm not getting into with this talk because the math starts getting kind of weird, but like the best fit is not linear, as you can probably tell. It's what's called an asymptotic model. Actually turns out to be probably what's really going on here. But in general, like once you start factoring more like spatial granularity, so stuff that's not at a 500 meter scale, so we have a better idea of like how much stuff's varying within each pixel, your model starts to really improve, which was sort of like a reassuring sanity check for what we were doing. And again, cloud cover is just kind of all over the map. Doesn't seem to help. But horizon, again, there's this clear delineation where like if you have stuff on that horizon, it's either reflecting or illuminating, and it just shifts things up in general, compared to like if you have nothing really on the horizon. And that was something that like this is one of the things we're going to get at when we're in this paper we're working on is like the role of direct glare versus scattering and trying to build a model of light pollution, and like what we kind of miss if we only use remote sensing data. All right. So coming back to data point, this is like this is one of the best examples I had of this. But like like we see stuff like kind of really vary like by a factor of 100 with each pixel, and then what we want to see is like how much does like do our measures of scalar illumination, like how much does it actually vary? Like what if we were to plot the variation with each pixel versus these satellite-based measurements, will we see any pattern? So like if we were just to collapse and sort of look at that variance with each pixel and compare it to the satellite-based measurements, what does it look like? So this is actually getting at, we were talking about like the coefficient of variation on the y-axis here. So each dot here represents like how much each pixel, like how much does that scalance vary within each pixel, and this is versus the sky quality atlas, and it turns out it's hugely variable. Like mostly I can tell you that under brighter sites it tends to vary a bit more, but one of the things we're taking away from this is it's really varies. Like each pixel is just highly variable. We have a coefficient of variation of like over 1. I mean, it just means that your standard deviation is larger than your mean essentially for the brightnesses that we're recording. So this is one of the things is like within each pixel, it's highly variable, and it tends to increase. It's not a strong correlation, but it is a positive correlation. Cloud cover again doesn't seem to help at all. Horizon does. Like literally just like this one's really clear cut. Nothing blocking you. It's darker than you expect. Stuff on the horizon, it's brighter than you expect. So yeah.
If I were gonna do a really dumb model,
Yeah.
let's say that the total illuminance is a factor of the number of equally bright lights that are scattered around the area that I'm measuring. And then you would expect, I guess, more patchiness at intermediate numbers of lights, right?
So some sort of like intermediate heterogeneity hypothesis. Yeah, in terms of heterogeneity, yes, but to some degree. But it turns out the big factor is like you just tend to get the greatest degree of homogeneity on places that are just flat beach sites.
Okay.
that's where you get the least spatial variability, independent of how bright it is. So you can have like a ton of sky glow, but if it happens to be like just flat beach, and there's not a lot of stuff blocking the horizon anywhere, that tends to be really uniform. Even if it is really bright, it's just uniformly bright. So that's why the horizon still seems to be this huge determining factor. Yeah. Now the difficulty starts to become like, how do you do remote sensing of like how much horizon you'd expect to see? Like, what would be your measure of rugosity? That's the fancy name for like, how lumpy is it? People in coral ecology use that word, and I didn't know what it meant for the longest time. I had to look it up. So now I get to use that word. All right, so rugosity. So like, I mean, is there any way you can tell from space like how like spatially variable it is? That's a more difficult question. It's not an insurmountable problem, but I don't know who's going to really do it for like some ecology project.
Radar interferometry.
The what?
Radar interferometry?
Yeah, or like microwave reflectance or something.
You can
like
get that kind of data.
Yeah.
Well, if you had a smart grid, you could tell both power usage and the GPS elevation of every smart grid location. So
Yeah, I mean, you can do some really creepy stuff like that.
That's how we do it in smart grids, right?
Yeah, I know, like-
to do creepy stuff.
I know.
To find wheat dealers.
I mean, I have a Google Fi phone. I've just given up. All right. I mean, like, I know they can hear me. Yeah. No, I'm a patriot. It's not Huawei. It's Google Fi. All right. At least I'm getting something for the creepy deal, like Facebook. All right. Save money on my phone bill. Okay. So it turns out like so you have this huge amount of variability on the local scale. Within each pixel, within each hemisphere, it varies a lot. So the spatial variability. So who here hasn't seen what a p-value is? Okay, I'll explain this. All right, spatial variability, how much it varies within each pixel is correlated with both the sky quality atlas. So you have an R-squared about 0.27 and Beers. They're both about 0.27, so you're really close. It's close to 0.3. The p-value being less than 2.2 times 10 to the minus 16. Essentially, the p-value just tells you like how likely by random chance you're seeing this. Less than 2.2 times 10 to the minus 16 means like this is the probability this is a random that you're seeing this randomly. Okay. The amount of sky blocking the horizon seems to explain about half of the variability in sky glow versus the amount of cloud cover, which is only about 13% of that variation. So that, like, how much stuff is blocking the edge of the sky, you know, whether, again, it's like some sort of structure or illuminating structure, seems to explain a lot of that variability of, like, what you see in the overall image of the sky. But, you know, 0.27, like, well, okay, I can tell you, like, if one goes up, the other one's going to go up, but it's not that good of a model. But again, this is using, like, the drop-dead linear model, really simple. It turns out it's going to be a little more complicated than that, reassuringly, because like who wants to read a paper about I did a linear model? No, this is going to be an asymptotic model, and everyone's going to be really impressed, especially the Review Board of Frontiers in Ecology, and hopefully they'll see this video. Okay.
So one thing about your axis. Your x-axis, is that a log scale too?
For which one?
Like all of them?
Sky Quality Atlas
Your
is
Cloud Atlas one. Yeah.
this one's a linear scale, and then the y-axis
Is log.
well, that's coefficient of variation, so that's linear, but these I had to do log on that because the scalar illuminance varies. That grows. That's a huge.
But if your Cloud Atlas was logged, would it fit better? Because it looks like it should be log scale.
Well, so it turns out like if you, so it's an so the best model that fits the two is like is an exponential decay towards an asymptote.
Okay.
Yeah, is what it turns out to be, and the reason being is there seems to be like roughly above a certain level of brightness you see from space, you start to hit a saturation point with light pollution.
I see.
So this is one of the interesting questions we're starting to get at with this paper right now.
Yeah.
As we're writing it, is like, okay, like how universal of an asymptote is this?
Yeah.
Is there like there's a locally defined value, or is there more of like a global like limit, like, oh, you'll tend to see this in Singapore or Tokyo or LA, where it kind of starts to flatline. Like at a certain level, like no matter how bright it looks like from space, it's only going to get so bright on the ground for the most part.
Okay.
Yeah. There's an R package for that too. Okay. So this is kind of the fancy stuff I was using for like how much does it vary? So like, this is an image of the night sky. You see a really bright light there. So how much does the actual each night sky vary by brightness? So this is some of the other stuff I was playing around with here. So we get hemispheric variability, which apparently no one's done in any sort of light pollution study, surprisingly. So this is actually, this is the first time I used calculus in life since I was in college. And I had to figure out how do I chop up the night sky into 40 equal area sectors So I guess my calculus teacher was right. I will use this one day. So I divided up into 40 equal areas, and the reason being is that if I want to look at the brightness in one and like use it to calculate like how variable it is, I need to have equal areas. Yeah, so that was fun. All right, so I did this with every image, so all 515 images, divided every image into 40 sectors and looked at how much they varied by like the amount of brightness in each one. And the y-axis is coefficient variation in scalar luminance. This is within each image. How variable is each image? And this is compared to how bright it is. And in general, roughly, things get more variable when they tend to be brighter, just because you tend to be in more urban environments. Cloud cover, again, is useless to me. But anyway, it just is all over the place. But like, yeah, brighter areas tend to be more variable. It's not a strong relationship. What? Oh, sorry. Yeah.
Sorry. I think you're short of time. I'll ask later.
I'm short of time. No.
No, I just wanted to ask, like,
Oh, yeah.
when you're cutting up the previous graph, right?
Yeah.
So in that, instead of like, taking these pies and then going in circle, if you had just taken all 40 pies, would that make a difference? Because I don't think they would have. I mean, are these within pies the way you have cut it? Would they also have the same?
Yeah. Oh, yeah. So like, it was divided by. So you have to calculate what the bands of right ascension are as you go from the top of the sky down. So you divide it into. So the way it is like 8 sectors going by right ascension going around the sky, and then 5 bands going from the horizon to the top, such that each square project on the sky has the exact same area.
So the way you are cutting it up is important in the way that you have
Yeah.
defined this.
And the reason why I did that, and like this data is going to get thrown up to like for other people to look at, is because then someone could also start looking at how much does it vary by right ascension. So how much does it vary going around one direction versus going around the other direction? Yeah.
That's important.
Yeah. So someone else is probably going to want to use that. I just want to look at just whole sky, like how much just in general is it going to vary. But that's the reason why I divided it both by right ascension and declination.
Oh.
Yeah. Okay. So going back to like, how much does it vary, like it turns out, so horizon actually has somewhat more of explanatory power going on here, and in general, again, it's just brighter means more variable a little bit. Okay. So, why this is important. So it turns out, like, if we do, like, so we look at the Sky Quality Atlas, it's better at predicting what we see on the ground, because we're using a couple more factors, better spatial resolution. That's 0.39. If we just use VIIRS and we don't use any of the sky quality meters or anything like that, we're only explaining about 30% of the variation. Again, it's only using a linear model. It turns out if we use that fancier model that I'm not getting into, like that asymptotic model, you get about 80% of the variation. And I think there's something going on there. So I think that's really what's helping improve it. So you're combining both remote sensing and field data. And what the thing we're trying to figure out now is if this works over an area as large as Southern California, can someone get away with using this in somewhere for like Oregon? So they don't have to do what I did. And that's one of the things we really want to see is like other people to like try to use our model and just sanity check, does this work? Cloud cover doesn't seem to explain as much as we thought. The idea was that cloud cover seems to amplify light pollution to some degree because it reflects backlight, and in really dark areas it actually reduces light pollution. But for the most part, like the assumption is it should amplify it, but it turned out not to be nearly as powerful an effect of just stuff on the horizon. And that's something that like no one's really talked about in any like big study looking at remote sensing data. All right, so why are we all doing this? It's because of the aminals. All right, great. So technically, I'm an ecologist, so I have to care about living things. And that's what this data is for. How is this affecting these two species? Why these two species? Well, we're looking at coastal environments, and these are both like found in Southern California. The western snow plover is a relatively rare bird, and it's really sensitive to a lot of anthropogenic stress, so noise, light, and all this sort of stuff. And one of the things we want to look at is, can we start to use our light pollution maps to better predict where things are migrating to? So if things are either attracted or repelled by light, can we use this to predict how ecosystems are adapting? Are things avoiding us? Are they attracted to it? And then the California grunion, same deal. And we want to look at these, one terrestrial, one aquatic species, because we're looking at coastal environments and we want to see, does it have the same effect in either environment? All right, where are grunions? Okay, So one of our undergrads was really cool. He got a fellowship to work with JPL, and JPL has a team that's looking at trying to model where the grunions are. I forget why, but anyway, the grunions. I don't know if you know, like there's these fish, and they have these big migratory patterns, and they spawn. And we think they have some. It seems to be tied to lunar cycles, and it accidentally ended up in the middle of a grunion run last summer. It was really cool because I was out there taking photos. It was out like way the northern edge of LA County. And I was just out there with like a headlamp taking photos, and all of a sudden I saw a bunch of other people like rushing out there, and I kind of got worried because I thought like, oh, this is like a private beach, you can't be here. And it turned out they were just like running out in the ocean and scooping up fish. So the grunions seems to be like a lunar cycle, and so the idea would be if light pollution is throwing that off, because if it's really really bright, are they going to be able to detect the moon as well, if that's what they're reacting to? Or here's one of the other things that's really interesting: do they not care? Are they adapting? Because this is one of the things that light pollution's been around in some significant amount for 100 years, and your generation time is roughly a year. That's enough time for evolution to really start to kick in. Something should start happening. You won't see it with humans because they only have really 3 generations out of light pollution, but like 100 generations, we should start seeing something. And so that's one of the ideas, like, well, are the fish adapting? Do they not care? So this is one of the things we want to look at is we have positional data on grunions, we have our light pollution model, and how much of like where they happen to show up has anything to do with light. And the answer is nothing. That's still interesting. So reassuringly, no matter what happens, this will still be an interesting paragraph in the paper. All right, where are plovers? Not nearly as widespread because they're really skittish. I think, well, I didn't see the western snowy plover taking field data. There's some other plover I saw that I guess nobody cares about down in San Clemente. But this is like in LA County, this is their known roosting sites, and again, this is we want to see like how well we can predict bird numbers from the light pollution levels, because they're really sensitive to that. And one of the things we're trying to do is habitat, like people are doing habitat restoration, especially like as you get down towards Rancho Palos Verdes, there's like a lot of work that's being done to try to like at least restore some of the coastal habitat. All right, so that's a habitat vector. As much as like any other sort of resource, because again, you're using it for signaling or all sorts of other biological processes, and it's going to reshape ecosystems. And it may actually be chopping up habitat in essence, because if you have some areas that are really bright next to areas that are relatively dark, and you have a lot of this alternating pattern, you actually are chopping up the habitat in the same way that freeways are for some species. So that's one of the things we want to start to see, because it may be causing these sorts of effects on a relatively local scale. So we're looking at that with plovers, we're looking at this with grunions, and we're gonna play around with a bunch of fancy spatial models. One of them is called MaxEnt. I'm sure there are others. You know about any, Brad? Okay. Yeah, it's MaxEnt's like one everyone seems to use, so I guess I'll use that one, and then we'll pass review. What was that?
Somebody sent me something.
Okay. Okay, got it. So this is, so what we want to do is like, if you were to like overlay a map of light pollution, you overlay a map where these species are, does anything line up? And we have some evidence because there's some preliminary work looking at mountain lions, and you can better predict where the mountain lions are actually migrating through the Santa Monica Mountains by looking at the areas that are relatively dark and relatively quiet. So, those of you who know anyone who lives up in the Hollywood Hills, just let me know that. All right.
Make lots of noise and turn on the lights.
Yeah, pretty much. Although they are really majestic creatures, like when they stuck into the LA Zoo and ripped off a koala's face. I mean, they're cats. That's what they do. Okay. So, think about your house cat was the size of a mountain lion. It would be a mountain lion. All right. So, light pollution in the third dimension. So, we're looking at things that are migrating like up and down the coast. Now, the next part, this is the third part of our project, is doing some experimental manipulation, things that migrate up and down the water column. So, a lot of things like in the oceans migrate up and down either for daily cycles, so light, dark. So phytoplankton, for example, like they'll migrate up to the top of the water column, photosynthesize, migrate back down to avoid being eaten. In this case, though, we're not looking at phytoplankton. We want to look at something that's a little easier to measure: marine fouling organisms. Yeah, it's. Look, I didn't make the illustration. Yeah, it looks like a Daphne eye, but so marine fouling organisms, crud. Okay, so like things that migrate up and down the water columns. One of the things there's some preliminary data that suggests that a lot of these, like if you're in a harbor, like all this stuff that just congregates on the surface, if you have higher amounts of light, they'll tend to settle faster. And so one of the things we want to look at is, all right, can you see this effect in really, really bright areas? And can you experimentally manipulate this? And are there different subspecies now of these like marine fouling organisms, barnacles, that are adapting to levels of light pollution? So those that have lived in these really bright areas like the Port of LA have become desensitized to light. That would be kind of interesting to see. Because there is we do have some evidence in other systems like insects that seem to get desensitized. So we're actually going to do the experiment. This is running right now in the port of Long Beach. So we have these plates. We just gray plastic plates we set out underwater. Some were just blasting with extra light, some were not. And they're just sitting in the port, and we want to just compare like light versus dark, just how much stuff grows on it. And then we're going to take plates and we're going to put them in a really dark area, probably Catalina Island, and repeat the experiment, and essentially see like, do you see the same pattern? And is there evidence of adaptation going on in the really bright areas in the port, and can you experimentally manipulate it? But one of the things we want to see is that if you're in a really bright area, does adding extra light make any difference at this point? Our hypothesis, probably not, at least at those levels of light pollution. So we're going to compare these settlement rates. This is not the biggest part of our project, but this is like just something we're adding on, just to get preliminary data for what would probably be like phase 4 or whatever. But this is what the plates look like. They're just like these gray plastic plates. We set up some solar power lights. We're putting them out there. So the Boy Scouts of America there's a part of the port that they're letting us use this on, which is great, because then we don't have to go through like 20 different port authorities for whatever reason. But we still had to get remote powering for this. So we have these solar power dock lights. We have this string of these plates hanging out underwater, and then we're going to come back in a couple of months and just see basically like how much crud grows on them. And this is taking a really long time, which has been really annoying for me because these things have been floating out there for months. And not a lot's growing. And this is one of the interesting questions is why, and either is the water just super polluted, or has it been relatively cold and then it's just the growth rates are slow because it's cold. And this is one of the frustrating things about science and why PhDs take forever. But we will drag these up, and then I did promise the high school students who were helping me take data that they would get to count these lovely piles of crud to help measure what's going on here. Still waiting, sorry. Anyway, you got your letter of rag, so I held up mine in the bargain. Okay, so anyway,